For today's lecture, we're going to be talking about differentiability of functions of several variables. So differentiability for functions in higher dimensions is trickier than it is in one dimension. So we'll talk a little bit at the end of the lectures about that because it has to do with the limits. But for our purposes, most of the functions that we're going to encounter are okay. We typically only encounter these problems really seriously around or close to singularities. We're in two dimensions, being differentiable is the same as the graph of the function having a good tangent plane, in the same way as in one dimension, it's the same as having a good tangent line. So for example, if we have a function in 1D that's not differentiable, then there's no really good tangent line that we can draw next to it that'll match up with the slopes and for both the possible directions of approach, for example. And in 2D, we might have a shape that has some kind of corner in it that makes it so that there's no really good tangent plane that'll match up with all the directions of approach. So differentiability in higher dimensions has a similar problem. But let's talk about differentiability for functions of a single variable first. We're going to shuffle the definition around a little bit so that we can come to a conclusion about how this is going to work in several variables. So the old definition says that a function is differentiable at x if this limit on the left-hand side exists. So the limit as h goes to 0 of f as x plus h minus f of x divided by h is equal to some constant number, m. So this m is going to be the slope of the tangent line, or the limit of the slopes of the secant lines as we approach this point, x. And that's the limit is going to be the same thing as f prime of x. Now, we can rephrase this slightly by changing our focus. Instead of saying, let's let h go to 0 and look at f of x plus h, we could just say, let's take the limit as our point x approaches the point a. And then we're just taking f of x minus f of a on top. That measures how far apart those are, the rise of the function, divided by x minus a, the run on the bottom. And if that limit exists and it's equal to this number m, then that number m is going to be our slope as well. So that's a second version of this. But I'd like to adjust this even more by moving m over to the other side and bringing it into this quotient. Now, this is the same definition in principle, but on top, what we've got is this function, f of x, our function, minus this linear function. This is a line. We're taking our function minus the formula for a line and then dividing by x minus a. This line here is then going to be the closest line to ours if this limit is equal to 0. So this is a definition of differentiability for single variables that's phrased slightly differently. It says that this difference between our function and the line goes to 0 very quickly. It doesn't go to 0 just full stop. It goes to 0 faster than x minus a does. And that's the definition of being differentiable that we're going to generalize by turning all of the numbers into vectors, and by replacing division of numbers we can't really divide vectors, so we're going to divide lengths of vectors. So here's our definition of differentiability in several variables. A function is differentiable at a if there is some matrix M out there, which we think of as our slope, so that this limit of f of x minus this linear function, f of a plus m times x minus a, is going to 0 more quickly than x minus a is, in the sense that this ratio tends to 0 as x goes to a. So here, x and a are vectors. We're talking about a limit as one vector approaches another, so we have to be a little bit more careful about that. When this limit exists, the matrix M is called the derivative matrix. It's going to be a very useful concept, and we'll talk about it further in a minute.